Welcome to Ragtime. This is a place where we dive deep into the world of retrieval augmented generation, or RAG. Hey, Mike, welcome.
Thanks, Pamela. Hi, everyone. Today we are going to do a deep dive into various methods you can use to optimize your vector index for scale.
Exactly. But before that, we have a special interview with Pablo and David where they'll talk about the real world impact of optimization techniques in enterprise AI. Over to Pablo and David.
Hey there, everyone. I'm David Smith, Principal AI Advocate for Microsoft Developer Relations, and welcome to this exclusive conversation with Pablo Castro, CVP and Distinguished Engineer at Microsoft working on Azure AI Search. Now, in previous episodes, we've looked at retrieval augmented generation and search, but now we're going to dive down a little bit further and look at the real world impact of optimization techniques in enterprise AI. Pablo, thanks for joining us. Why don't you tell the folks a little bit about yourself?
Hi thanks for the introduction, and hi everyone. I'm glad to be here. As you mentioned, I work in the Azure AI search team. This is a super interesting time to work on information retrieval and kind of help establish the connection between everything that's going on in language models and how do we ground it with the data that our applications or our organizations use to get stuff done. So looking forward to talk about how optimization plays a role in this picture.
All right, that sounds great. So let's dive down to that, dive down into that a little bit. And we already know that search is a really important component in AI applications. But why do we need to care about optimization? Optimization is quite a broad term, but when it comes to enterprise AI, why is optimization important?
There are multiple dimensions to it. Like in general, one of the things you want to do is make it so that when a solution is working well, you are not afraid to scale it. You want more users, you want more data, you want everything that could be useful for the application or for the users of the application to be in there. And for that, one of the things you have to do is make sure that when you scale, you don't have to worry about costs or latency or accuracy. And all of these dimensions are forms of optimization. So there is you build a little demo first to inspire the ideas and get people thinking. But then when you take this to production, then all of these scaling dimensions play a role. One of the things I always see with customers that have built successful solutions with this is, as a developer, you sit down, write this application, put it out there. You never know, but when it goes well, one of the things people ask is like, how can we get more of this? Like, I want all of my organization's data or every element of data that my application handles to be behind maybe my chat interface or my generative interface, maybe for authoring or things like that. And back to the other point, like this boils down to how do you make it so that you're not afraid to scale it, and optimization plays a critical role in that picture.
Okay, so I heard a few aspects there. You talked about scale, you talked about accuracy, and you talked about cost. Can you give us some examples kind of to motivate those of examples you've seen in the real world where those aspects have become important in a certain application and how optimization plays a role in addressing that?
Yeah, absolutely. Like let's take scale and cost, which I often go close together. One of the things that you face when building generative AI applications is, first usually you focus on quality. So you go like, let's put all the details of the data we have into my retrieval system, my search engine.
And when you say quality there, you mean the quality of the response from the AI?
So you want to combine, like ideally, maybe you have documents, maybe you have pictures, maybe you have rows or other forms of data. And ideally, you would put all of that in your retrieval system so that then the AI can interact with it and answer the questions that your users are asking. Now, when you do that, modern retrieval systems use like a mix of techniques. They use this vector-based retrieval using kind of these embedding models. They use traditional retrieval systems like keyword search and whatnot. And those things grow over time. And so to use the example of vector, which is vector-based search is very popular these days. These things get big. So as you have more and more volume of data, then you can push either on the scale of the system or the economics. Now, one of the things that we see in the wild that are very effective is a variety of techniques for vector compression, where you can significantly reduce the size of your vector index by applying these compression techniques while keeping all the same data. Of course, you enter these interesting trade-offs where when you compress stuff, these are lossy compression techniques.
Yeah.
So you trade it for something. Maybe you're trading it for accuracy that you can recover later with other steps, but you need to have that in the picture. We do see this out there very often, where especially scenarios where a developer would build this application that maybe has tens of millions or hundreds of millions of vectors in the system. So if you can do a 4x or a 10x compression ratio over that's a huge impact on your ability to scale the system, and or put it the other way around, is maybe it's 4 to 10 times smaller, so it has a huge boost in cost.
Okay. So as I understand things, the large language model that's at the center of these AI applications, it can't see all of the data that you have in your database at any one time. So there's a process here, if I get things, that you need to select out the most relevant data for the AI to generate its response. Is that right?
That's right. Like, the model knows what it knows, from its training data. And the whole point of this RAG pattern is that you bring whatever extra data you need to answer a particular question, and you have to choose which data to bring, which is maybe another dimension of optimization, where you may have a very large kind of knowledge base of documents or data of some other form, but you have to pick the top few that will be most relevant to answer a particular question, because you can only fit so much in the context window of a model. So in that sense, the ability to find the best candidates for grounding an answer, the best candidate kind of pieces of information in your knowledge base to ground a particular answer, it's absolutely critical. And with scale, this becomes more and more important. The more documents you have, the more content you have, the trickier it is to say, hey, I have 1 million documents. Give me the 3 that I need to ground this particular answer. And that's something that we put a lot of energy on as well in the work we do, and in general, kind of when you use a RAG-based application that feels really good, it means people have put a lot of work on quality of retrieval as well.
Okay. You mentioned the context window a minute ago there. Let's talk about that a little bit, because when I ask a question, say, to an AI application, you, in the architecture of that application, load in information from Azure AI Search and provide that in the context window, which is a limited amount of information that you can provide to the model in addition to the question or any other information that we want to provide it about tone and so forth. So you've got a limited space, is what I'm trying to say, of information you can give to that model. Can you give the developers some tips about sort of how to choose that balance between, perhaps lots of subsets of many documents or a few particularly relevant documents? How do you choose what to actually put in that context window?
Yeah, I mean, you're spot on. This is an area where there's so many moving parts. Usually, you have to factor the many aspects into this. So first, usually it's not just the retrieved content you have to fit into the context window. All your instructions go there. If it is a chat interface that you're building, so you have a little bit of chat history, including all of chat history may not be practical, but you usually want to include enough of it that kind of gives a little bit of context to the question. And sometimes you also want to include examples, this is few shot style prompting, and then the grounding data. So that's one aspect, is you have to kind of have a plan of how much you use for each one of these different parts of the prompts you build. The other dimension is there's a lot of work that shows that different language models deal differently with very long prompts. In particular, in many cases, models tend to kind of pay less attention to the middle. There is this very good paper called "Lost in the Middle" that quantified this loss for some models. So too little content, maybe just not enough to answer the question in an appropriate, well-grounded way. Too much content may throw the model off. So this is an area where you have to experiment a little bit and kind of try to be methodic about evaluating what is the right amount of context necessary for your particular application scenario.
Okay, that's an interesting angle right there, because I thought, part of this new revolution of models with very, very large context windows, millions and millions of tokens, pages of documents, if you want to think about it that way. What prevents me from just basically dumping everything into a very large context window and then asking the AI to process that? Sounds like you had one aspect there.
Yeah, there are multiple aspects to that. So first of all, I should say there are some cases where that works, and then you save a whole bunch of work. Just put the whole content in the context window and ask away. And if you can do that, then why complicate things any further? Now, in practice, there are many scenarios where that doesn't work. So, for example, sometimes your data just doesn't fit. Like, we have many customers that have this multi-million document knowledge base where each document is many pages. You have a few million of them. That just doesn't fit. Second, the latency of the interaction with the language model depends largely on the length of the prompt. So if you put 1,000 pages worth of content and you go back and forth each time, then that's not going to be a snappy experience.
Yeah.
And then lastly, again, very long documents tend to cover many topics or many aspects and whatnot. And if you have the opportunity to use a separate system that has been custom built to take the parts of the document that are relevant on each interaction and only present those to the model, you're stacking things in your favor in terms of getting better answers. And the description of a thing that picks the best candidates, that's what a ranking system is. And that's what search engines, sophisticated search engines have at the top of their stack, is a re-ranker that would pick the best candidates for any given question or conversation.
All right. So now I think I get it. So you want to choose the best candidates to provide in that context window for the model to make its answers. But that takes time, I guess. And until you provide that information, the model is just not responding to my question. Now, I know you work on Azure AI Search, and that has some features to help with that. Can you talk a little bit about how Azure AI Search solves that problem?
Absolutely. So I would say, as I mentioned before, optimizing these things is this multidimensional problem. So I'll pick on three aspects. You have to choose on quality, what is the bar that you want to hit in terms of the quality of responses. Also, there's an aspect of latency, how fast you want these things to go. And then there is a performance aspect, how cost effective you need these things to be. So one of the things we do in Azure AI Search is we try to pick the best defaults so you get the best trade-off between all these dimensions. But also, we know many developers are experts in this space and want the control. So we give you all the building blocks so you can choose the right mix that is right for your application. To give you an example, we support multiple vector compression techniques like quantization or Matryoshka embeddings, where you can take kind of prefixes of vectors. And we also support right out of the box a sophisticated ranking system that can run on top of the core retrieval part, and it significantly improves results. And we also support this at multiple scale points. So we'll pick good defaults for you, but if you want control, you can say, this is what type of quantization I want to apply on my vectors, and this is I want some amount of, for example, oversampling to rescore a little better later. And I want, say, to use the semantic ranker, which is Azure Search's kind of most sophisticated ranking model. So you can pick and choose, and that puts you in a different part of this kind of multi-way spectrum of options for quality.
All right. And I know we're going to dive down into some of those options in the segment to follow. But before we get to that, any final words, Pablo? Like maybe look to the future. Are there any trends in AI optimization that you see coming down the pike in the near future?
There's so much going on these days. I would say first is it's very valuable as a developer when you build these applications. When you're ready to scale them, think about all the tools available to you. What you did for sketching the application is about kind of thinking about what's possible. What you do at scale may push you into thinking about all these other options about compression or quality of retrieval and whatnot. Second, I would strongly recommend everyone to also not only build the app and look at the initial results, but find the right ways to evaluate whether you're getting the right trade-off between speed and quality and whatnot. In the end, you want your users to love the application that you built, and for that, they need good answers. So scale and the quality go together in kind of getting that done. And in terms of looking forward, we keep working on making so that quality out of the box keeps getting better and better. So you have to do less and less work to get things right. And that's a trend that I think is going to continue. The emergence of agents also means that now you don't have just this kind of single shot retrieval models that or application patterns we saw in the past, but it's more of you have these autonomous systems that as they're doing work, they need to know more about your organization or your context in order to get the job done. So we see the same challenges of retrieval in the middle of language models applied not just to single shot kind of question and answer scenarios, or chat style scenarios, but also in the middle of kind of agent workflows. So I think we'll see a lot more in that space as well.
All right, well, that sounds awesome. Certainly, as an AI engineer, having to do less work is always appealing. So look forward to hearing more about that in the segment to follow. Thank you so much, Pablo, for joining us today. Everyone, do check out the show notes for Ragtime on GitHub for lots of links to a blog post with lots of details about the techniques that Pablo was just talking about and links to some case studies. But with that, let's dive into optimizing vector indices for scale. And that's over to Pamela and Mike. Thanks, everyone.
Thanks, David and Pablo, for that great discussion. So, Mike, can you tell me more about the options available to optimize vector retrieval?
Sure. So first, let's talk about how Azure AI Search handles vector data. We support a wide range of data types from single precision floating types, where 32 bits of information per dimension, all the way down to a single bit. The total size of a vector is the number of dimensions times the size of the data type. In this simple example I have here, let's say we have a vector with 3072 dimensions with 4 bytes per dimension, or a single precision floating point. That vector would be around 12 megabytes. So by default, we store 3 copies of each vector on disk and then consume that total of the total storage available to you. 1 copy is for the vector index that's loaded into memory for fast ANN searches. This copy is also limited to the max vector index size, which is another quota you should be aware of, which is around 20 to 30% of the total storage available in your service. We can optimize query performance and increase the number of vectors you can fit into memory using some techniques we'll cover in a moment. 2 other copies of the original full precision vectors are also stored on disk. One is used for rescoring, which significantly improves the quality of results for a highly optimized vector index. The other is to support retrieval or merges, where you don't want to include a copy of the vector when other fields in the document are updated. You can elect to not store either one of these, so you have full control over how much data is actually stored to disk, depending on your scenario.
All right, so given all those dimensions and sizes, what are the various techniques for optimizing vector storage and reducing those sizes you talked about?
Sure. Since your vector index size is limited, one of the techniques that's great is called quantization or compression. You could take vector data and lower the precision of the data type from whatever is provided by the model. It could reduce, for example, a 32-bit or 16-bit float down to an 8-bit integer, lowering the size of the vector by up to 75%. It identifies a range of numbers and creates bins from the minimum to the maximum and divides them into 256 bins, because that's what fits in the data type, and gives each bit a number. And then the value of each vector dimension that it finds is rounded to the nearest bin. Binary quantization is similar, but it reduces the vector down to a single bit per dimension, which is then packed into a byte. This can provide significant storage reduction, and you can offset the effects of compression by adding oversampling and rescoring over your uncompressed vectors that are stored to disk.
All right, so this quantization reduces the size of each number in a vector. Can we also reduce the dimensions of a vector somehow?
Yes, you can truncate your dimensions if your model has been trained to support MRL, or Matryoshka representation learning. This technique produces embeddings where lower dimensions contain more information and higher dimensions can be truncated without a significant loss of semantic information. Binary quantization, together with MRL and setting the stored property to false, provides maximum vector index size reduction.
That's really cool. So that's only for models that were trained with MRL, like the OpenAI text embedding 3 models, plus some open embedding models like Nomic. So how much size reduction can you actually get from these techniques?
Sure. So yeah, referring back to our previous example, with all the optimization techniques we've discussed, 1 million vectors from the OpenAI text embedding 3 large model can be reduced from 11 gigabytes down to 122 megabytes, a 96 times decrease in the size of the vector index loaded into memory.
Whew. All right. So all this size reduction is great for costs and presumably for speed of queries as well. But reducing this precision and truncating the dimensions, it's got to affect the quality of the results. So how can developers still retain high quality results?
Sure. Yeah, we definitely see a reduction in quality due to all of the loss of precision and truncation. That's where we bring in oversampling and rescoring. So oversampling pulls more candidates from the vector index, and then the rescoring will order those to get the best candidates using the unoptimized original vector stored on disk. These optimizations will then work together to give you the most cost-effective scale with minimal impact on the quality of results.
Okay, so this all sounds really cool, and I love learning about this. For me, it always helps to see what these options look like in code. And your colleague Farzad put together a great notebook that anyone can try out. So let me actually go through that notebook now, so we can see the effects of all these compression options. So here's the notebook, and the first thing that it does is set up a connection to the Azure Search Service. And here's just an example search index configuration that has a few of these options that Mike just talked about, right? So this is setting up an index that has a couple fields. We've got the ID, which is the primary key, and then we have the embedding, which is a vector type with 3,072 dimensions. And it says it's using this vector embedding profile and not storing the embeddings for retrieval purposes. So then we can see this vector embedding profile here, and it is connected to a algorithm configuration and a compression name. So the algorithm that it's using is HNSW. This is a type of ANN search that Mike was describing, right? So ANN meaning approximate nearest neighbors. So it's a way of doing a more efficient vector search. And HNSW is incredibly popular for vector search these days. It's very efficient and very good at finding great results. So it's setting up HNSW with cosine distance as the metric. Then for compression, this one is doing a binary quantization, which is most extreme, going all the way down to 1 bit, truncating the dimensions with that MRL down to 1024. And in this case, it is not rescoring and it's discarding originals. So this is a really extreme compression here. So this is just to show you in code what it looks like to define a search index and to experiment with these different options. Now, for this notebook, it actually tests a bunch of different compression scenarios so that we can see the results. So let me show you the table here. All right, so we've got 1, 2, 3, 4, 5, 6, 7, 8 scenarios that we're testing. So we start off with the baseline, which is basically just has none of those techniques that Mike talked about, right? And it's even storing the embedding. And so when you see stored embedding, that means it's a copy that would get sent down with your results when when you're asking like give me all my fields so then I can like do something with them. And most times for RAG, we don't need to have that stored embedding because all we need to know is what are the best results, and then we go and we look at like the text in them and we send that text to an LLM. So most of the time we really don't need to store that embedding. So we definitely want to encourage people to turn that off if you don't need it, because it'll really store, save some space. So then we have baseline S, where we don't store the embedding for our results. Then we've got scalar quantization, and then scalar quantization with MRL down to 1024, and then discarding the originals. And then we go to binary with 1024 and discarding the originals. So we've got these 8 different scenarios that we can test out and see what the effects are on the size and the quality. So then we have some code that creates the indexes. So, a bunch of code here that creates the indexes. And then we need to put something in this index to test it out. So for this notebook, it's bringing in DBpedia, which is a bunch of Wikipedia entries. And these have all already been embedding using that OpenAI text embedding 3 model with 3,072 dimensions. And so it's really important to know what the model is, because we need to know whether it's capable of supporting that truncation dimension with MRL. And in this case, since it's an OpenAI text embedding 3 model, we can truncate the dimensions. So we can try out that feature. So we bring in all that data. We can look at the data and see like, okay, here's the Wikipedia article for parabolic reflector, right? So it's bringing in a bunch of different Wikipedia articles. And then we can also see this embedding here, and you can see it, these have very high precision to start off with, and we don't necessarily need all that precision. All right, and then we take all those documents from Wikipedia and we upload it to all of our indexes. So this actually does take quite a while to do all this uploading, because we're taking 100,000 documents from Wikipedia and we're moving them into 8 different indexes. So I ran this yesterday, and certainly won't be running it right now because it'll take some time. But basically, we're uploading the documents to the index. All right. And finally, we want to go and look at the index sizes. So now that everything is uploaded in indexes, we can actually use the Azure Search API to retrieve the statistics for each of our indexes. So we can see how much we're actually using up of our storage sizes and of our quota and all that, to decide, what sort of compression techniques we might want to use. So we go ahead and display that in this table down here. So let's take a look at this, because this is super, super interesting. Here's our baseline. So our baseline is requiring about 3,800 megabytes of space for the main storage. And then the index, which is the HNSW index vector size, that is 1,200 megabytes of space. Now in baseline S, that's where we don't store the embedding, and we see a big decrease in the storage size here. So we go from 3,800 to 1,300. So that's 65% storage size reduction. So that's really significant. So if you really consider that option there, it's a good option. Now, if we look at the HNSW size, the index size is still the same, because this stored embedding was only affecting what came back with the results, wasn't affecting what was in the index. So our index size does remain the same. Now, when we go to scalar full, this is where we're taking those 32-bit floating numbers, those really long floating point numbers that we saw, and we're reducing them down to 8-bit integers. And the interesting thing here is that our HNSW size goes down by a bunch, right? From 1,200 to 300. That's a big reduction in the index size. So we're taking up less space there, and also should get faster queries. Our overall size actually went up from the previous one. And that's because when we do that scalar quantization, by default, we keep the originals so that we can use it for for rescoring. So it's still got some originals in there. And so that size actually goes up. But we're getting faster queries. And a lot of times that's can be really important for us, right? Then we can truncate the dimensions to 1024. So our storage size goes down a bit there. Also, our HNSW size goes down a lot. So now we're down from 300 to 100 megabytes. And, that's a huge reduction from our baseline, 91%. And then we can also look at the binary options. So those are similar. And it's where we get our most extreme reduction in size, all the way down to 17 megabyte. That's a 98% reduction in the index size. And we also get a 96% reduction in the storage size if we discard the originals. So you'll see the storage size is the most affected by discard originals, because it doesn't have to keep those originals around. But we'll also see that affects the quality quite a bit too. So now let's talk about the quality, right? How can we determine whether the quality of the indexes are good? So a good practice is to have a bunch of queries and you run a bunch of queries, you look at the baseline results, and then you see how the retrievals, the results change as you change your compression options, and then decide, am I still getting high quality results? Am I still getting the number 1, number 2, number 3 results that I want from this query? So for my example here, I'm searching for the first avian dinosaur in the fossil record. And, I start off with the baseline, and I can see okay, in the baseline, Archaeopteryx is number 1. That's what I would expect. It's the classic one that everybody thinks of with that question, or at least that I think of. And then we can see, the other options. And the interesting thing is that you can look and see as you go, to more and more compression, we see actually the same 5 results all the way up to scalar truncated 1024. So even with 8-bit integers, 1024 dimensions, we're getting the same exact results. So that's really promising, right? Now, when we discard originals, which means we can no longer do that rescoring with the originals, that's when things start to get a little worse, right? So here we're seeing some different ones in the top results. We're seeing some resorting there, and we may not be comfortable with that, right? Similarly with binary, binary also actually, even binary truncated 1024 amazingly has the same results as the baseline, which is really, really impressive. However, when we do discard the originals, we once again lose the quality of the results and see some new ones that we haven't seen before and see the number one move to number two. So when I look at these, for this data, I think, all right, I think we can get away with binary truncated 1024 as long as we keep the originals. And then I would feel comfortable with it. But this is something that, a decision that you can make when you're making its index. And the cool thing with AI search is that you have all these options that you can play with and figure out what's going to work best for your index size, your retrieval needs, for your RAG scenario. Really, really cool. Let's go back to Mike. Is there anything else that developers should be doing to improve the quality of their search results?
Yeah, that was an incredible demo. Like, you could also improve the quality by using some higher order features that are integrating with vector search. These are using some features from our keyword search side of the product. And you can do hybrid search, which does results together with keyword and vector. You could use semantic ranker, which will re-rank results based on our highly optimized semantic models. And then a new feature currently in preview, query rewriting, will make the query more effective by adding additional relevant search terms and then refining those results.
Awesome. Those are great options. I always use hybrid with that semantic re-ranker for my RAG search indexes and tell everybody about it. You can check out the previous video to see a deep dive into those search options with Matt and Nitya and explore more about them. So thank you for sharing all your knowledge with us today, Mike. And now I'm going to hand over to Nitya to summarize everything we just discussed with a doodle.
Let's recap what we learned about in optimizing your vector index. Vector storage can be expensive. Think about it in terms of the number of dimensions and the storage size per dimension. We need optimization to scale. Quantization reduces vector size by reducing the bytes stored per dimension. Scalar quantization reduces storage per dimension by a factor. For example, float32 vectors can now be stored as 8-bit integers, trading off precision for storage size. Binary quantization goes further, storing a single bit per dimension, where that bit indicates if the stored value is lower or higher than the centroid for that dimension. The Matryoshka representation reduces vector size by reducing the dimension count. For example, it truncates higher dimensions without a significant loss in semantic quality. MRL and binary quantization together provide optimal compression. For example, an OpenAI text embedding ADA 003 based vector solution that has 32 bits per dimension and 3072 dimensions can now be reduced by up to 92% by storing it in 1024 dimensions with 1 bit per dimension. So how can we maintain quality with scale? Compression is achieved at the cost of precision. We can recover it with oversampling and rescoring strategies, giving us cost-effective scale with nearly the same quality. We also saw a code-based walkthrough of the entire process. Don't forget to check out the notebook in our repo to try this for yourself. Finally, we can do further quality recovery by using mechanisms like semantic ranking and query rewriting, giving us comparable results in quality with substantially less storage overheads.